I'm going to work a couple of problems on our practice 17 for module 9. This is the first practice set for kinetics. If you want to see other problems worked, please just post your questions on the discussion board. I'm going to grab number 5 first. So here we have a question. I'm looking at a chemical reaction, and I am looking at asking about the disappearance of N2O5, which is right there, given the rate of appearance of NO2, which is right there. Now, in the lecture videos, I worked it one way using formulas that related the two. It's actually just stoichiometry, so I'm just going to work it with stoichiometry. This is a slightly different way than the lecture videos, but they both get us to the same answer. I want to know what is the rate of disappearance of N2O5. So how does the concentration of N2O5 change with respect to time? If the NO2 is changing by 0.373 molarity per second, and that is the concentration of NO2 with respect to time. All right. I'm going to convert from NO2 to N2O5 using the mole-to-mole stoichiometry here. That is all this is. If I have moles of NO2 on bottom, that will cancel with the moles of NO2 in that molarity unit. I want moles of N2O5 on top so that I'm left with concentration of N2O5, which is a molarity, and then I'll use the stoichiometric coefficients. So I have a 2 on top, a 4 on bottom, and I punch that in my calculator. Be sure you're doing it along with me. 0.373 times 2 divided by 4 equals. So that is the molarity per second, because that's the units we're expressing this rate in. Whether it says appearance or disappearance just has to do with whether it's talking about a reactant or product. Don't worry about that. Don't worry about the sign. Give some thought to the sign in the lecture videos, but we can just ignore all of that. And we want the correct number of sig figs. This guy has 3 sig figs. Remember that these are exact. These are whole number ratios. They're not rounded. They're exact. So I need to go to 3 sig figs. And so I will type in my answer of 0.187, rounding that 6 to a 7 because of the 5. And it is molarity per second. All right, so that's one problem. Let's go back here. Let me scroll down. Let's look at question number 7. A certain reaction is third order with respect to Cl2 if the rate of this reaction is 1.6 times 10 to the minus 3. When chlorine concentration is this, what's the rate when the chlorine concentration is that? All right, I'm just going to work this here. So I know that it's third order with respect to chlorine, and so the rate law is rate is equal to K times the Cl2 to the third power. That's what third order with respect to Cl2 means. So there's 2 ways I can work this. I am given the rate of the reaction. That's the rate right there. I'm given the rate of the reaction with a certain concentration, which is right there. I can calculate K and then turn around and use K in the formula to answer the question. What is the rate of the reaction? What is the rate of the reaction when this concentration is there? So I can actually do that. So 1.6 times 10 to the minus 3 is the rate. That equals K times the 0.1 cubed. And then solve for K. You should be punching this in as I do it to double check me. I get the K is equal to 1.6. And so I want to know what is the rate. The K is a constant, so it will still be 1.6. And now I'm going to change my concentration to 0.2, and that is cubed. So times 0.2 cubed, I get 0.0128. Let's see, that's that guy rounded to 2 sig figs. But there's a second way to work this. And the second way to work this is recognizing the patterns. So as I look at this, since it's a third order, come back to this, the rate will increase proportionally to the change in the concentration of the Cl2 cubed. So if the concentration of Cl2 goes up from 0.1 to 0.2, it doubled, then the rate will go up by 2 cubed because of the third order. So that cube is right there, and that's how the rate goes up. So the rate will increase by 2 cubed, and so the new rate is equal to the old rate, 1.6 times 10 to the minus 3, times 2 cubed. And so 1.6 times 10 to the minus 3 times 2 cubed is 0.0128. I get exactly the same answer. So you can work these problems either way. The second way, understanding how that rate changes as the concentration changes for a certain order reaction, is better in the long run because it is applicable to more types of problems. So there's a second problem from our homework, our practice. I'm going to scroll on down and catch a third one in this video. All right. Similar kinds of question. I've got a reaction. I'm told the orders of that reaction. I'm told a rate at certain concentrations. I want to know what the rate constant is. Very similar to what we just did in the sense that I can write a rate law. Rate is equal to a rate constant K, which is what I'm trying to find. First order with respect to A and second order with respect to B. That's what that first sentence means. I am given a value for the rate. The rate is this, and the concentrations are this. Calculate the rate constant. It's just a matter of plugging this in. So I have 420 molarity per second. Notice it says don't worry about units. So there's my value of rate. That equals K times concentration of A is 0.03. Concentration of B is 0.02, and that is squared. And I solve for K. So let's punch this in. 420 divided by 0.03 divided by 0.02 squared. And I get that K is 3.5 times 10 to the 1, 2, 3, 4, 5, 6, 7th. All right, I hope that helps.